So today we'll continue our discussion on LP modes, step index fiber. So last couple of classes we sort of derived the mode profiles and the conditions for the mode to exist and how to calculate the propagation constant. Right. So today let's look at the mode profiles. Right, so again, so recall that the modes can be written as, right, so the electric field as a function of position, right? So this, so it's a linearly polarized mode, so it will have orthogonal degenerate modes with orthogonal polarizations. Right, and then so there was a radial part. So we could have some field amplitude then. Right, so we had indices L and M. Right, so the index L goes with the Bessel functions, right, of order L, and then the radial part is the Bessel function, right, which depends on. So the argument of the Bessel function, recall, so this U depends on the propagation constant beta, which is a solution of the transcendental equation. Right? So for, as we saw yesterday, we could have a number of solutions to that equation for each L, right? So that is denoted by the index M. So for each M, we'll have a unique value of beta and a unique value of this two. Right, and then the angular part, as we saw, was just either so cosine or sine. Again, so these would be two different degenerate modes. Right, and then the Z dependent is just the phase. Right, so that's how we write. We can write the mode profile for the LP mode with index L and M. Right. So how do they look? Right. So for example, if you plot the radial part, so how the mode profile looks as a function of increasing distance from the center to the core. So the only radial dependence here is just the Bessel function. So right, if we denote this by some R of R. So if you plot sort of the intensity profile in the radial direction, right? So like that, as a function of R. So we denote this to R by A. So one will be core cladding interface. So say one is somewhere here, the core cladding interface is somewhere here. Right, so this is core, and this is cladding. Right, so LP01, so the radial part, yeah, is the Bessel function. We already saw what the Bessel function looks like, right? So for L equal to 0, we have the 0th order Bessel function, which you know starts from some value, right, at the origin and then goes down. So LP01, so for M equal to 1, which is the fundamental mode, right, the lowest order mode, that looks something like this. Right? So the form is J0, right? And basically there is no, it's sort of just, so you know that the LP01 is the fundamental mode, right? So this argument here doesn't reach the first root, right? So basically, this doesn't cross 0. This just asymptotically sort of. So I mean, in the core, it's this Bessel function of the first order. Of the first kind and nth order, or for 0 it's the 0th order. And then after this becomes a modified Bessel function here, right? So it just sort of expands again. Now, for example, if you go to LP02, right? So m equal to 2. So you know now that happens once we pass the first root, right? So there will be a point here where this goes to 0. The Bessel function goes to 0. So there will be 1, 0. Right, so it looks something like this. So this is LP02. So there's a 0 here. So there's a point inside the core where the field goes to 0. Right, so in general, basically, if you look at the LPLM mode, it will have m minus 1 zeros in the radial direction. Right, we're excluding the origin. Right, because so for L greater than 0, you know that the Bessel function for L greater than 0 starts from 0 at R equal to 0. So excluding that, there will be one more, there will be n minus 1 zeros along the radial direction. So for example, now let's see what LP11 would be, right? So LP11 again, so that will be J1, right? And since m is 1, so there won't be any zeros in the radial direction, so it will just so do this. Right? So LP11 has a null at the center. So maximum intensity actually occurs slightly away from center. Or in other words, if you look from the cross section, it will sort of look like a ring, right? With a null in the center. Now 2, right? So that again will start from 0 because that will be J2, right? And now 2 means m is equal to 2, so again we'll have 1 0.
The screen is not visible.
Okay, is it back?
Yes, sir.
So LP22, right, would look something like this. Next one is LP22. So starts from 0 as a peak, then has another 0, another. Okay, and you can see that how much the mode leaks into the cladding. So that sort of goes up with increasing L and M, right? So for a given L, as M increases, the mode leaks more into the cladding, or as L increases, also the mode leaks more into the cladding. Right, so LP01 is the most confined mode. Okay, so that's how it looks in the radial direction. Now, if you look from the cross section, right, into the cross section of the fiber, because so there is also a phi dependence here, right? So you can see from here, so for a cosine alpha or sine alpha dependence, as we go from phi to 0 to 2 pi, because L is an integer, right? There will be 2L zeros in the phi direction, right? So you can see, so look at again the cross section into the fiber, right? So now if you look at LP01, so LP01, L is 0, so there is no phi dependence, right? And region dependence is just sort of looks like almost like a Gaussian function, right? So it just looks like a blob here with maximum intensity in the center, right? And the field is linearly polarized. So, right? So again, so it looks like that, right? So sort of the height of the arrow is denoting like the strength of the field. Right, so there are two degenerate modes, either that or that, right? So we call this Y and this X. So this will be the Y polarized mode and the X polarized mode. So this is the fundamental mode. This looks the simplest looking mode. Almost it just looks like a Gaussian field. So now if we go to LP11, so now we have here cosine phi or sine phi, right? So now we'll actually have four possible combinations, right? So either X polarized cosine phi, X polarized sine phi, Y polarized cosine phi, Y polarized sine phi, right? So only LP01 is twofold degenerate because there is no phi dependence, but for all other modes, for L equal to 0, LP0M modes have twofold degeneracy, but for all L greater than equal to 1, they have fourfold degeneracy. Right, so we'll have four possible mode profiles here. So first let's take, so for example, if we take Y polarized cosine phi, so cosine phi means right, so if this is X and Y, so this is the phi direction, right? So this is phi equal to 0 and this is phi equal to 90. So cosine phi means it's maximum at 0 and then 0 at 90. So we have sort of two blobs here, and phi equal to 90 degree has 0. There's 0 along phi equal to 90. Okay, and the polarization is again Y, right? So so it goes negative here. So here the field is pointing in the opposite direction. Right, so this is the Y polarized cosine phi. So for X polarized cosine phi, basically the blobs are in the same place, the polarization direction is different. It looks like that. Then you could have Y polarized sine. So the blobs now look like this. Right? So 0 is along phi equal to 0 and phi equal to pi. Okay. So let's look at now, for example, LP21. Right, so now this will be cosine 2 for sine 2 phi. So there will be 4 blocks now, like 4 zeros along the azimuthal direction. Right, so again, this will be the y cap. So the mode profile looks like J2 right. So there's a null in the center because of J2, and there are 4 zeros, right? So cosine 2 phi means, so when phi is pi by 4, that's 1 0, right? And then pi by 2 plus pi by 4. And y cap means it looks like this. So every time you switch to another block, the phase flips. Right, so this is the x cap. And then now we have sine, then blobs will look like this. There will be zeros along pi to 0 and pi to 90. Right? So if you go to 2 2 now, there will be like a 0 in the radial direction, right? So there will be like an additional blob now. So there will be another 0 in the radial direction, right? If you go to 2. So you can see for high LNMs, there will be like a lot of sort of blobs in your field profile. So there are some pictures in the books you can take a look. Also online you can find nice picture these modes. Okay, yeah, so that gives you an idea of how these modes look. Right, so again, just to emphasize again, so for L equal to 0, there is only 2-fold degeneracy. For L greater than equal to 1, there is 4-fold degeneracy. Okay. Right, so given any L and M, it should be straightforward to draw the mode profile. Right? Should be able to do that. Now let's just take a look at the strength of the longitudinal component, so the z direction, right? So LP modes we started with assuming that like in the weakly guiding approximations, the modes are almost transverse, so PEM, and the longitudinal components are negligible. So let's see from the solution if that actually works out. Right, so we did this for the slab also. Remember that we calculated the longitudinal component and saw that if the index difference is small between core and cladding, then the longitudinal component is small compared to the transverse component. So recall in the beginning when we were discussing how to find the modes. So for example, if we start from an X polarized LP mode, so we have EX, we solve for EX, right? Which gives us the solution that we just looked at, like the Bessel function times sinusoidal function. And then using the Maxwell-Curl equations, right? So we first find the H components, right? So for example, H, Y, and H, Z, and then using these H components, again using the curl equation, we can find Ez. Right? So recall that using that, we could find Ez in terms of Ex like this. Right, so basically the longitudinal component depends on the derivative of the transverse component with this factor here. Right, so now again, so beta lies between K0 N2 and K0 N1, right? So if this is really if N1 is very close to N2, right? If the index contrast is small, then here we can sort of, without losing much accuracy, we can just say, let's say, for example, this is K0 N1, right? Because so let's say this is 1.5 and this is 1.49. There is not like the percentage change in beta that can happen from K0 N2 to K0 N1 is like much less than 1%. So basically the magnitude of the longitudinal component is so beta magnitude is something like K0 N1. Here we have K0 N square. So here we are left with the K0 N and the magnitude of this derivative. Right, so now again from the solution, so we know that this is like the Bessel function. Right, and so at times we have some sine or cosine, but that only varies between 0 and 1. Right, so let's say the maximum value we can take is this. So now if we take derivative with respect to y, right? So this is function in terms of the radial coordinate, so we can write it as a derivative with respect to r and then del y. So for del r by del y, we write r as square root of x square plus y square. So you can see that del r by del y you get as y by square root of x square plus y square, which is y by r, right? And if I write y as r sine phi, right, the relation between Cartesian and polar coordinates, this is just sine phi. Okay, so this factor is just sine phi. And then for the derivative, we get a derivative of the Bessel function times this constant out front. So right, so then we use this for the derivative here, then the ratio So if we take the ratio of the longitudinal to the transverse components, okay, so this thing is less, so sine phi is always less than 1, right? And u by a, so recall u was a times square root of k naught square n1 square minus beta square, right? So this is sort of like right, and this here, the ratio of the derivative to the Bessel function, that's of the order of unity, right? So recall we had these relations. So the derivative of the Bessel function is another Bessel function of an order differing by 1. And if you look at the Bessel functions, right, they're all of sort of similar magnitudes, right? So you can also see from, for example, the transcendental equation where we had equations like this, right? JL prime by JL equal to KL prime by KL, and then when you plot them, the values that you get are sort of close to unity. Okay, that so the magnitude here is somewhere close to unity, at least to order of magnitude. Right, so then basically the ratio is sort of roughly given by this, and then so this again beta is greater than k naught n2, so the maximum value this can take is, if I put k naught n2 here, right? So then you can see this will become right, or this basically is square root of, and this is basically, if you recall, 2 delta. Right, so basically what we're saying is that the strength of the longitudinal field divided by the transverse field is less than this. Right, so if you look at the notes from the slab, we got a very similar result for the slab also. Okay. And so again, if this delta is very small, then our approximation of neglecting the longitudinal component is valid. So as I said, for typical fibers, delta is less than 10 to the minus 2, 10 to the minus 3. So then the LP modes are quite accurate. So we'll see that in the next couple of classes, we'll see that the LP modes are not the exact solutions as we have discussed already, right? But again, when delta is much less than 1, then they're quite accurate and sufficient for most purposes. That's why I study it, because they are much simpler to handle than the actual vector modes as they are called. So we'll briefly look at that in the next couple of classes. But yeah, so this shows that this is a good approximation for small delta. Okay, so next let's look at the power flow and sort of the confinement factor, which is how much or the percentage of the power which is confined in the core, right? So when we drew these radial mode profiles you could already sort of see that the lower order modes with lower L and M are more confined in the core compared to the modes with higher L and M. But let's try to quantify this confinement factor. Right, so again, we start from the field profile. So for example, let's take a Y-polarized mode. Right, so this mode profile here, we saw it looks something like right, so for R less than A plus R greater than A times either right, so again, just like for the stab, we start from the pointing vector, right? So in the z direction, the propagation direction. So again, sort of we take E cross H star in the z direction, so that will become from, since we have Ey, we have Hx. Right, and again from Maxwell's curl equation, we get Hx as right.
So that line is not visible.
What is not visible here? This one?
Yes, sir.
Yeah, so I mean, it's just the same mode profile that we've already written down many times, right? So in the core, this Bessel function J of the first kind, and then in the cladding, it's right. So again, so from the Maxwell's curl equation, del cross E, right? If you take the x component, then get this. So we plug this in for Hx here. Right, so we get the quantity which is proportional to the mod square of the field, as expected. Okay. So now, for example, if you want to find the power in the core, then we just integrate this pointing vector in the core region. Right, so right, so R goes from 0 to A, and phi goes from 0 to 2 pi. So we just plug So in the core, it's this, right? So let's take a cosine phi mode, but even if you take sine, you get equivalent result, right? So yeah, so we have an integral over the radial coordinate and then over the azimuthal coordinate. So if we write, so this cosine square as 1 plus cos 2 by 2, right? So only this, the constant part will give us a non-zero value for the integral, right? So this integral is this pi. And then to evaluate this integral, so we will change a variable. So let's say this argument here u r by a x. Right, so we rewrite this integral in terms of x. Right, so we get an a square by u square from here, from this change of variable. And then now we have a standard Bessel integral here, which is x times jl square of x. Okay, so there are standard Bessel integrals which are have been evaluated. Just like, for example, for sinusoidal functions, you have a lot of integral identities. Similarly, you have for Bessel. So, for example, this integral here can be evaluated as this. Okay. So yeah, using that result, you get the power in the core. Okay, so you can see, so this factor here, beta mod a square times 4 omega mu naught, that's the same factor we got for this lab, right? So that just relates the field amplitude to the power units, right? And then we have pi a square, which is the cross-sectional area of the core, right? So this is like some intensity times area. And then here we have some expression with the Bessel function, so that gives the dependence on the mode, right? So all this is independent of the mode, but this here inside the bracket depends on which mode you're looking at. Okay, so now to find the confinement factor, we also need to evaluate the fraction of power in the cladding. Right? So basically, now we evaluate this integral in the cladding. Right. So then for cladding again, phi goes from 0 to 2 pi, but the radial goes from a to infinity. Right? And then the expressions that we use, so here instead of j, now we have k. Goes from a infinity. Again, this integral for the angular coordinate gives me pi, same thing. W equals to W. Okay. Right, so yeah, so we get for the cladding. Okay, so sort of this basically the same expression here, except you replace J with K and U with W. Okay, and the integral limits of course change, so now this becomes W. Okay, and again, so you have for this modified Bessel function also a similar relation for the integral. So, okay. So what that basically means is that okay, so that's for the cladding. Similar expression, but J's have been replaced with K's and then U with W and then also the sign is flipped. Okay, so the total power guided in the fiber, that's the sum in the core and the cladding. Right, so total power like that. Right now, so these expressions should be somewhat familiar, right? The transcendental equation that we got had similar expressions with J and K. So specifically recall right, so we had these two forms for the transcendental equation. One was JL plus 1 by JL W times KL plus 1 KL, right? And the second one was JL minus 1 by JL is minus WKL minus 1 by K. Right? And so these terms you can see they're sort of like the product of these two, right? So if I multiply these two equations, on the left hand side I get something which is JL plus 1 times JL minus 1 by JL square, which is this. Right? On the right hand side I have KL plus 1, KL minus 1 by KL square. Right? So basically what we are saying is this thing we can write as minus W square by U square times KL plus 1, KL minus 1 by KL square. Right? So that our final expression will just be in terms of K, or equivalently we could write it in terms of just K. So we plug that in and then um, 1 plus W square by U square okay, so now here we have this, so W square plus U square, is V square, right? So this thing is just V square by U square, right? So can replace this by V square by U square. Okay, so that gives me the total power. Right, so again now you can see so I have something which converts the amplitude to intensity times area, and then we have V number of the fiber also coming in, and then dependence on the mode profile. Okay, so the fractional power in the core, which is known as the confinement factor, right? So we have an expression for the total power and an expression for the power in the core. So we can define a confinement factor right, which is the ratio of right. So if you want a well confined mode, then we want this eta to be close to 1, right? As close to 1. There's a question because if we take sine function, yeah. So remember the integral for that azimuthal direction was just integral of cosine square from 0 to 2 pi. If you take sine, that integral has the same value, right? Integral of sine square from 0 to 2 pi is also same. So it doesn't matter if you take sine. And recall they are degenerate modes anyway, right? So there should be no difference in their properties in terms of like power carried, etc. So yeah, you get the same. Right, so then if you just do this, then so these constants cancel out, right? So on numerator we have 1 minus this JL plus 1 JL minus 1 by JL square, right? Which we can again use this relation and write it in terms of K, because the denominator here we have in terms of K, right? So you can write this as Okay. So just sort of simplifying this a little bit. Right, so we get this expression for the confinement factor. Right, so again it depends on the mode profile, right? So the confinement factor for different modes will be different from here. So now we can sort of compare how the confinement factors for different modes look like. Maybe I'll be out of time. Yeah, okay, maybe we'll discuss in the next class. We're out of time. So next class we take this expression and then for different modes plot this confinement factor, for example, as a function of V number, right? And so we'll see that. So you get different curves for different modes. So for a particular V number, right? So for example, a particular fiber, we'll see that modes with lower L number are better confined, right? So they have higher confinement factor for the same V number. And if you take one particular mode, as you increase V number, right? So that's, for example, equivalent to increasing the size of the fiber at a particular wavelength. You'll see that with increasing V number, of course, the confinement factor also increases. The mode is like increasing the size, the mode is more confined in the core. But yeah, we'll continue next time. Any questions?
Hello.
Is there a question?
Yes, sir.
Yeah.
Sir, am I
Yes.
audible?
Yeah.
Sir, I like it's not related to today's class, but I have a doubt in general. So,
Yeah.
suppose we have an optical fiber and whose refractive index of the core is constant, but the refractive index of the cladding is varying uniformly with x, and the limits within which the refractive index varies are lesser than that of the core refractive index. So, sir, does it affect the performance of the optical fiber in terms of power, output power?
Yeah, so first of all, like that's a very strange kind of optical fiber you're talking about. But remember, like if the fiber is well designed for a particular wavelength, right, that means that most of the power is in the core anyway, right? So the power into leaking into the cladding is very small, right? For example, in other words, this eta is close to 1. So the cladding, right? So for example, you're talking about instead of like, for example, a profile like this, right? So this is R, this is A. So you have N1 and N2. You're saying that maybe this is something like some varying refractive index here in the cladding, right? So that's fine. That should not change too much the performance of the fiber because, as I said, for the well-confined modes, most of the power is within the core anyway, right? So that will only change your mode profiles a little bit depending on how much this. So it's like a graded index in the cladding now, right? So, but the effect will be smaller than what like for example, we looked at a graded index in the core. But if you have graded, if the index is constant in the core, but graded in the cladding, the effect will not be that much, right? Because most of the field and the power is in the core, and the field in the cladding is anyway small, right? For confined nodes. So it might change, for example, some properties like, for example, cutoff, right? And the exact propagation constant values slightly. But again, that change will be small, better confined. So for lower order nodes, the change will be negligible. But if you look at some higher order nodes, maybe which are less confined in the core, then the change will be a little bit larger. But yeah, usually practically that kind of fiber is, unless you have some special situations, not really.
Sir, actually, in the book, there was a question that we remove a part of the cladding, and instead of cladding, we pour some kind of liquid of unknown refractive index, optical fiber.
Yeah, so you can see, right, what, right, so what that means is basically you're changing N2. What
So
they
the
are saying is,
refractive index was not constant. It was somewhere between 1.3 to 1.5 it was given, but not the constant refractive index of the cladding or the liquid.
yeah, but if you want to exactly solve for, I mean, if you have some refractive profile here, Nx, then, for example, if you want to exactly solve for the modes, then you can do the same way, right? Like, for example, what we did for the gradient index, we solved in the core, and then in the clad, we took some boundary conditions, right? Similarly, again, you have to do the same thing. You have to solve, so you take a constant index here, solve for the mode, but then take gradient index and then take boundary conditions. But
Okay, sir.
as I said, practically, like the effect that it will have on the modes will be like negligible if for lower order modes which are well confined. For modes which are leaking out into the cladding, for example, like this eta is less than 0.5 or something, where half the power is in the cladding, then it can make a difference.
Okay, sir. Thank you, sir.
But, yeah. Right. So typically also, so the way this, how fast this mode decays here into the cladding, right? So that depends on this gamma or the W that we have, right? So that depends on this index contrast. So if the index contrast between N1 and N2 is larger, then this falls faster. Okay? If the index contrast is smaller, then this falls slower, right? I mean, you can take the limit, for example, N1 is equal to N2, then there should be no variation at all, right? It will be like one medium. So as now you start decreasing N2, then you have some mode profile and it starts falling. But as the difference increases, the mode falls faster and faster. So you can also look from that perspective, right? So now if you change the refractive index profile here, so for example, if you have some refractive index profile like this, compared to something which doesn't immediately change but slowly changes like that, then the field, like for this slowly varying, for this gradient index here, dotted line, that will fall slower compared to this step index, right? So for the step index, it will fall faster. Because the index difference is larger. So there are some qualitative arguments like this that you can make. But if you want some exact values, of course, then you have to solve for modes.
Okay, sir. Thank you, sir.
So yeah, for example, here you can sort of qualitatively say that the confinement factor. So if you take a step index fiber, remove the cladding and have some fluid or something which has a gradient index, then the confinement factor will go down because the mode will start leaking more. If this index now is slowly varying. On the other hand, for example, if you just remove the index and just have air around, right? What that means is now what effectively you've done is make this step bigger, right? So now instead of going to N2, now you want to N air, which is 1, right? So this is like, let's say 1.4 something. So if you just remove the cladding and then just have a suspended core in air, then actually that acts like a fiber with larger index contrast. Okay, so in that case, the mode will go into the core. But again, that is valid up to some what can I say? Some value of this size. If you make the size smaller and smaller and smaller, then of course it will start leaking out again. But yeah, if you keep the size the same, just remove the cladding. So it depends. If you have some fluid which has a slowly varying refractive index away from the interface, then the mode will leak out more. If you have air, then the mode will go in. So it depends on what. Any other questions? So there's one question, can it have larger skin depth? I don't know what you mean by skin depth, but if you're talking about this, how much this mode is leaking into the cladding, if that's what you mean by skin depth, then yeah, that's what we discussed.